Hello everyone, it's March 13th. Yesterday the contest didn't do very well. Actually, pretty badly. I mean, I didn't start from the beginning. Was only able to solve 3 problems with 1 error, and the last one, I got a bit distracted. My cat was a little bit distracting, so wasn't able to really do the last one very well. And yeah, so that was that. But yeah, to take a look at the rank, I think the ranking would be pretty poor. Maybe yesterday was 2,000 something. Yep, same 2,500. Yeah, it was pretty bad. So anyway, so today the goal was to, finish this and go back to the last question. And I don't have a good idea of how this one can be done. I might create a solution that will time out, but I don't really think that's necessary to try. Or maybe we should try, even if it's going to time out. And maybe we should. I don't know. I mean, I'm gonna do this one first. Oh, this is the easy one. Check valid parentheses. Ooh, so many times I've done this before. All right, so a stack. All right, this is just a stack problem. Yeah, let's just handle this one really fast. Wait, hold a second. We have, yeah, the time zone is different now. We're at daylight savings and I have 2 hours left. Huh. Oh, does that mean the contest for next week starts from, actually I don't know. Let me add to my Google Calendar. So kind of take a look when it start. Maybe it starts earlier. Oh, no, it starts later. Damn, it starts 1 hour later. All right. Yeah, I don't like daylight saving time at all. Okay. All right, back to the problem. Valid parentheses, right? So the goal is to create a stack, and every time we add something to the stack, we will check the top of the stack, or not add something to it. Every time we encounter a left, we push it into the stack. Every time we encounter a right, we check the top of the stack. So we set up a stack, right? And then we say for letter in S, if letter is in all left parentheses, then stack dot append. I don't say push. Else, right? Then we say if not stack, or stack the top, so -1, is not equal to letter. What are you talking about? Not equal to letter. Now we need to create a paren. So if the left, I need it to be right. If it's this, I need it to be this. If it is this, I need it to be this, right? So if stack, the top of the stack, is not equal to, well, actually it's going to be paren. The top of the paren of the top of the stack is not equal to letter, then we return false. Otherwise, stack.pop. which means they're equal, right? Now just pop, and then keep going. Eventually it will return true. That shall suffice, and I am not intending to test it here because I have confidence. We can also run an example of just this, or just this, and let's run an example like this, right? This, something like that. All right, let's try. Oh, wait. That's not good. Which one? True, false, false, false. True, false, false, false. Oh, this one. This one. No, wait, no. It's this one. So we should return. Return. Not stack. So at the end, stack has to be empty. Yeah. Try this one. There we go. I'm pretty sure that's probably one of the wrong answers I had in the past. Yeah, it's the good case of trying, so test cases. At the end, if paren is valid, stack must be empty at the end. All right, this is what, number 20. Use stack. Pay attention to the case where the loop all passes, but there are elements remaining in stack. $54, $28. I want to see what type of solution I got in the past. That'd be interesting. Is that the same? Yeah, it is the same. That is better. Yeah, this is a better setup. But it is the same. All right, so we're done with this one. All right, let's go back to this one. Let me put this one up. Yeah, I kind of half-heartedly tried a solution, but it didn't really work. I mean, I was thinking we go from a source and we go to the end, and we find the shortest distance, right? So that's my thinking. If we can go from the source 0 to destination, and along the way we will encounter many things, and eventually I find source 0 to destination, the minimum distance. Now the thing is, if during this, I can also record the path, right? I have the path and I have the weight. So if in this path the other source is in it, right, then it is guaranteed that if it's going to be source 0 to something to source 1 and to its destination. So with this, it is the shortest from source 0 to destination. And then it's not possible to go from source 1 to source 0 and then to destination, right? Because that's always going to be longer. So in this case, the only other possibility So we cannot go from source 1 to source 0. So because there are only 3 possibilities. Source 0 to source 1 to destination. Source 1 to source 0 to destination. Or source 1 to a intermediate, source 2 to an intermediate, and then to destination. Now the intermediate can be the destination itself, right? These are all the 3 possibilities. So what I claim is, if from source 0 to the destination, the shortest, the minimum weight already includes source 1, then it's not possible to go from source 1 to source 0 to destination, because we know source 0 to source to destination is including S1, right? Including source 1 already, and that's the minimum. So if I go source 1 to source 0, then we're going in circles, right? We're going in circles. Or if we pick another route, that would definitely be more weight. So therefore, if I include S1 from source 0 to destination, that simply means it's not possible to go S1 to S0. So this leaves only the possibility of S1, S2 go to an intermediate node, and from the intermediate node to the destination. Now here is the thing, right? Here is the thing. From the intermediate node destination, I need to know from source 1 to intermediate, I need to know from source 2 to intermediate, and I need to know from the intermediate to the destination. That's what I need to know. But that in itself requires a lot of computation. Like, I need to know from each node to destination without going through S1 and S2, right? That's the goal, because if I go through S1, S2, what's the point? S1 going here, and this has to go through S2. Wait, hold on. Maybe it does make sense. Does it go through S1, S2? The shortest path, that's what we're looking for. We're looking for the shortest path from any node to the destination. So we go from any node to the destination. What is the minimum weight? I mean, I can go through because I also want to memorize, right? We want to memorize this thing. That's the little bit tough part. So from each one, right? From each node, if I want to reach the destination without going through S1 on S1 on S0, right? So we have, let's say we have all these without going through. That can be done via memorization. This one can be done because the state is just don't go through S1, S2. Like, you just don't connect to S1, S2. And in that case, how do we, let's say we have that, right? And then we need to find from S0 to S1. S0 to S1. And then we need to find from S1 to destination, right? So from S1, if we go from S0 to S1 and from S1 to the destination, yeah, I don't know, man. I just feel like I'm not on the right track. From S0 to S1. If I go from S0 to destination, we find all this minimum path. And S0 is, so you cannot go back to S0, right? So everybody who can go through any other node, but don't go through S0. So yeah, that's the thing. If S1 is involved, then we have at least one thing done, and then, but I still need to investigate all the other possibilities. But each one, the cost is 0.1 to run this, right? The cost of running through this is O1. So if I go S0 to destination, that's O1. If I go S1 to destination, is also O1. But if I want to find every single node to the destination, the shortest path, that also O1, well, because every node is visited once, right? Every node is visited, so that's also O1. So I technically, by memorization, I can do that. So I can have every node to the destination, except like they don't go through S1, S2. And I can go from, how about from S1 to every single, no, you have to calculate S1 to every single node. That is going to take a long time. Think about this. If I find a path from S1, from S0 to destination, and S2 is on it, S1 is on it, is that guaranteed to be the shortest path? Yeah, so let's say from S0 to the destination, and S1 is on the way, right? S1 is on the way. Then that is the shortest. And the other way is if S1, S0 and S1, they go to intermediate, and from intermediate to the end, which means from S0, we will need to find a path to the end that does not include, right? Pay attention, that does not include S1, all right? So that means that's a longer path, right? That's a longer path. And then I need to go from, yeah, so that's not, if I can get S0 to S1 to destination, right? We have proved, so this is the shortest path. And then we have proved that from S1 to S0 to destination is definitely going to be more weight than the previous one, because this, if we go S1 to S0 and I go back to S0, S1, and then that's longer. If I choose another path, that's going to be longer. So it's going to be longer, or more weight. If I want to go S1, S2, go into an intermediate, and then go to the destination, that means we need to pick a path from S1 to the destination through an intermediate. And if I want to pick S0, right? And when we pick S0 is the shortest path we already found. Then we go S1, go into it, that's also longer. And if I want to pick another route, and it's already longer than this, right? So overall, if we can find from S0 to the destination or from S1 to the destination, it involves the other source, then problem is done. That is the shortest. That is the minimum weight. All right. Okay, so that is a good discovery. That's a good discovery, and we can run these two, right? Like what I have here, S1 to dest and S2 to dest. We can run this to obtain, right? We can run this to obtain the, how should I say that? We can run this to obtain the path itself, right? We can maintain the path itself. So at the end, I know what path we're dealing with, right? And if we take a look, oh, I have lots of nodes. But I can set up, right? I can set it up. I can set up such that I have a sentinel, right? I have a sentinel to know the weight and whether it's involved, whether the other source is involved. Okay. So with that in mind, if it's included, then we say that's definitely going to be the case. I think there's no other way can make it work. So now the third scenario, if we do S1 or I think it's called S1, S2, but yeah, it's called S1, S2. I don't know why I say S0. Yeah. So the other thing is S1 to destination does not involve. S2 to destination does not involve. They don't involve the other person, and we cannot combine the two, right? We cannot combine the two because if we combine the two, yeah, it's just not wise. Then what? Then what do we do? Okay, so let's suppose I have S1 to the destination. We'll go through a bunch of steps to destination, and that is the shortest path. And S2 will go to the destination, that's also the shortest path. And in order for these two, so S1 and S2, they need to join, right? So they either join at the destination, right? We join a destination. Or we can join somewhere along the line if they share, if the two paths share. So the earliest sharing, right? The earliest sharing will be the best. I mean, because think about it, from S1 to destination, I have the shortest path, right? I kept saying shortest path. It's not shortest path. It's a minimum weight. So if S2 wants to join this party, right? Want to join this party, I shall, because if I don't pick any of the things that's in it, all right, then the only way is I go a separate way to the destination, and that's just sum of the weights, right? But if I can join them, right, then the problem is which one I shall join, right? If I join earlier, it's actually not earlier or later because it is depending on the weight, right? If I, let's say, join early weight, I join early nodes, that you think, okay, I can save on the remaining, but that's a higher weight compared to join later, right? But that also means we have a, so would that be the case that the shortest path for the two, if they share, right? If they do share, right? Because the shortest is going this way, the shortest is going this way. If they do share nodes, then if they do share nodes, then the first node they share, then we should merge there. Do you agree? The first node we share, then we shall merge there. And I'm not sure. The first merge, then we shall share. The first merge. Because if we don't share the first merge, let's say, yeah, of course we just share the first merge because eventually we're going to return a path. If we don't share the first merge, then we are duplicating more weights, right? If we share this, then have to go this. We have to add this one as extra, and then we can save, right? So okay, so that's if they share. So we solved that problem too. If they share. Now the question is, if they don't share. They don't share anything, right? If the shortest path they do share, then we say we merge there. If we don't share, so that's the shortest. That's the minimum weight, and that's the minimum weight. And then they only meet in the destination. Does that mean there could be other paths, right? Let's say there's another path that they they share and then go to the end. So what we know is this path has higher weight than that, and this path has higher weight than that. But they merge, so the only cost is this path plus this path plus this, right? So if this costs more than this, but by adding this, it's actually the extra cost plus this is smaller than that, then there's actually, yes, it is possible that like if they share, okay, if they share, would it be more viable? Well, if they do share, if the two share, and I decide to, you know what, I want to share some other nodes, right? Let's say another node, if I share, will give me a shorter. So yeah, that's that. Maybe I can prove it. So if they say S1 and S2 share at subnodes, and this is the shortest, and both this is the shortest and this is the shortest. Now I say, if there exists some other node that they can share, right? Some other node that they can share, and then go to and then we say that one is the shortest and total. So this plus this plus this is smaller than this plus this plus this. All right, let's call it A1 plus B1 plus C1. And we know A1 plus B1, hold on, A1, B1, and C1. We know A1 plus C1 is the minimum to go from S1 to the destination. And B1 plus C1 is also the minimum, right? Now we claim that A2 plus B2 plus C2 is smaller than A1 plus B1 plus C1. What can we get? So we know A1 plus C1 is the smallest, right? So A1 plus C1 is the smallest and plus B1. And then we have A2 plus C2 plus B2, right? And we know A1 plus C1 is smaller than A2 plus, which means if we do A2 plus C2 minus A1 plus C1, in this case should be smaller than B1 minus B2. And this is a larger than 0 value, right? Which means B1 minus B2 is larger than something that's larger than 0. So which means B1 must larger than B2, right? B1 must larger than B2. But we have also shown, so we have B1 has to be larger than B2. And we know B1 plus C1 is smaller than B1, than B2 plus C2, right? B1 plus C1 is smaller than B2 plus C2. Well, in fact, B1 plus C1, because that is the smallest, right? That's the smallest, B1 plus C1. So another path, right? Another path B1 plus C1 is the smallest among all the B's and C's, right? Among all the B's and C's. So the question is it possible for B1 to be larger than B2? Because I know this is larger than this, and this is also larger than this, right? So what we have we know it's A1 plus C1 plus B1 plus C1. It's definitely smaller than A2 plus C2 plus B2 plus C2. This is for sure. Then we can confirm, we can say A1 plus B1 plus C1 is smaller than A2 plus B2 plus C2 plus C2. And this one is the cost of the cost 1 plus C1 is smaller than cost 2 plus C2, right? And then we want to see if it's possible for cost 2 to be smaller than cost 1. Well, if cost 2 needs to be smaller than cost 1, we say if this one needs to be small, and this is large, then C1 must be small, and C2 must be large, right? Because the first two must be smaller than the last two. And if it is large, then C1 must be... No, hold on. We're looking for possibility for the cost 2 to be smaller, right? So we look for this to be smaller. If this has to be smaller, then C2 must be very large. And C1 must be very small. Otherwise, because what we want to see is if C1 is larger than, we assume C1 is larger than C2, right? Therefore, C1 minus C2 is larger than 0, which means C2 minus C1 is larger than something, which is larger than 0. So C2 must be larger than C1. So C2 must be larger than C1. But that didn't make any sense. If C2 is larger than C1, hold on. We know this is larger than this, right? So the only possibility, so we know this is larger than this. So in order for adding this to make it smaller is this must be smaller than this, right? This must be much smaller than this. If this is much smaller than this, so much so that the amount of big then from this to this to this, would that be smaller than that? Hold on. This one to a second one to this destination. And this must be larger than this. If we so this is small. If this is smaller than this. No wait, hold on. If this is larger than this. If this is large, this is small. Right? Then if this is also larger than this. Yeah, if this is also larger than this, then if this is larger than this, and we want to make this, adding this must be smaller, thus it has to be very, very small. Right? Then we can say this plus this. So if this plus this is larger than this plus this, and this plus this is larger than this plus this, yeah, that's the thing. I don't know. So if this A2 plus C2, if B1 plus C1 larger than B2 plus C2, right? Then how about A1 plus B1 plus C1, A2 plus B2 plus C2? We say A1 plus C1, then plus B1 larger than A2 plus C2 plus B1. Right, that is true. And no, it is smaller. This one is smaller than this plus B1, right? We also know C1 plus B1 is smaller than A1 plus B2 plus C2. I'm going to try to find if we can find any contradiction. If this is larger than this, right? Let's say both sides add C1. We have A1 plus C1 plus B1 plus C1 is larger than A2 plus C2 plus B2 plus C1, right? And we know A1 plus C1 is smaller than A2 plus C2. Right, so this is smaller than this. So B1 plus C1 was larger than B2 plus C1. B1 plus C1, but we know B1 plus C1 is smaller than B2 plus C2. So if this is larger than this, right? It just means B1 must be larger than B2. If B1 is larger than B2, can that happen? If B1 is larger than B2, if B1 is larger than B2, then C1 must be much smaller than C2, right? So B1, C1, there's a B1 and C1, and then that's S2, that's destination, and we have a B2. So B1 much faster, so B2 is smaller, and B1 is larger than B2. And C1 must be much smaller, which means it will be something like this, right? This is smaller and this is larger, but the sum, this plus this, is still smaller than this plus this. Which is maybe possible. B1 and this. Oh, we have an example. 3 plus 2 is 5, right? And what I want is for B1 to be larger than B2, so B2 must be smaller, so B2 is 1. And we have this thing, so B1 is 3, is larger than this, and this is 5, so we can set this one up to 5, right? And then we can set up an A, so that's 6, that's 5, so we'll go A, we can, let's say 1 plus 2 is 3, and this is already larger than this, right? This is larger than this. And this is about 1 bigger. If it's 1 bigger, then this must be 2 smaller, right? This must be 2 smaller. Yeah, let's think about it. If this, right, if this is 1 bigger than this, right? If there's only 1 bigger than this, then in order for this to be smaller than this, then it's required that this, right, is A2 plus something plus 1 needs to be smaller than A1 plus something. So A2 must be smaller than A1 minus 1. So whatever this A1 gets, this has to be 1 smaller, right? This has to be 1 smaller. So let's say it's 1, this is going to be 0, right? It has to be, oh, so I have to be minus 1. And now we can make this, let's make this 2. This will be 0, right? So this will be 2, and that will be 0. So now we have 2, 3, 2. And the other one is 1, 5, 0. One plus 5 is 6. That's 7. It's possible. It's possible. So like if this is 0, and 0 plus 5 is smaller than 2 plus 2. It's be longer than 2 plus 2. And 3 plus 2 is also smaller than 1 plus 5. But when you add them together, oh wow, it is possible. It is possible to find a new one. Oh my god, this is different. Got you. Alright, let's check the hint. I've been thinking about this enough. Okay, I have this idea. I agree. I agree with this because if they can merge, it's definitely be better than if they do not merge. This is something we can show, right? Because they will have to merge. Either merge at the end, right? Or they merge earlier. Or they well, in that case, is that a merge? Yeah, that's actually merged. It's just the merge point is, it could be S1 or S2 is the merge point, right? They just merge. They could merge to a third point going down, or they just don't merge. Yeah, they have to merge. And then the problem is, where do we merge? Yeah, where exactly do we merge? We have so many nodes that we can try to merge, and then from that node we have to go one path towards the end, which means, but based on this, what we can think is find from every node to the destination the shortest path without going through S1, S2, right? We do that. And then from S1 and S2, we find the distance towards that node, right? So like from this node towards the end, if we have a certain value, right? And then we say from S1 to this, the shortest distance, from S2 to the shortest distance, and it should be shown that because this third part, it could be S1, S2, these two can be also, which means just if we go from S1 towards the end, then cannot go through S2. If we go S2 through the end, we cannot go S1. And if we go anyone else, we cannot go through S1 or S2. All right? Which is, that's fine, right? It's fine. Yeah, so because everybody start from, like, the case is to don't go through S1 and S2, but I can start from S1, which is fine, right? Which is fine. Which is fine because this one, you see, I add the node, so if it's already in there, it's okay, right? So then what I obtain is the distance for each node going to the end, and we can use memorization for this, right? Okay, so say we have that. I say we have that. Now the question is just from each one, from S1 to all the nodes. I need to know from S1 to all the nodes, or S2 to all the nodes, right? So from S1 to all the nodes without going through S1 to all the nodes. So S1 let's say from S1 to, but not going through S2, right? So from S1 to the first node, to the second node, that's O(n), right? We can do this in O(n) because every node is vid only once. Wow. Because every node is vid once. I go this, I'm trying to see how do I go. Like if I know that, wait, hold on. I want to know from S1 go to all the nodes, how, like the distance, the weight, right? The weight. What's the minimum weight to go to all these without going through S2? Yeah, I can do a DFS on this. Just go from S1 to reach as many nodes as possible. Yeah, we just go through everything as far as we can go and find the minimum distance. From S1, go to everybody. Okay? Everybody. S1 to everybody. And then from S2 to everybody. So we have those. And that is O(n) because I'm just traversing the entire graph. And then we want to find from everyone, go to the end. What's the shortest distance? And I already know because I already go S1 to the distance. So one is from S1 as a starting point and go to as far as I can go and try to find the shortest distance to a certain node, to every node, right? And then we go S2 to do the same thing. And now we're going to loop through every node. So we go from first node, one node to the end. What is the shortest distance without going through S1 or S2, right? Without going S1 or S2. Because if we go through S1 and S2, what's the point? Yeah, what's the point? We don't go through S1 and S2. So from those towards the end, everyone goes towards the end. And this, yeah, is also, so now I have a array from each node, right? But excluding S1 and S2, from each node going to the destination, we have the shortest distance from all of them. And I also have from S1 to every node, right? S1 to every node, the distance, I know. S2 to every distance, so these are 3 arrays, right? Now, what I want to find is go through everything. Okay, I have an idea. I have an idea. Let's try this. Well, first of all, this thing I want to change, right? I don't like how this one, a list. No, I don't like it. I'd like it to be a default dict, right? And that the key, right? So the key, and it's going to be another list with so I'm going to do a dict here. So for edges, right? Then we say adjacency is from, right? Is already a dict. So we say if t is not in adjacency list, aj ft equals weight. Otherwise, this ft equal to minimum w and ft. Okay, so now we're gonna define DFS. Right, DFS we don't need to know. Okay, we do not need to know the path. All we need to know is the distance. Okay, the distance. So what do? Well, we want to find from S1 to everybody. So what we need to do is pass a. Well, in this case, there's no target, right? There's no target. So we have DFS1 is towards a target. DFS1 is towards a target. I want to know, and we need scene. So from a node towards a target, and we want to know the shortest distance from a node, right? And we shall have a dp. Okay, so in this case, we want to find from this node towards the target, right? What's the shortest distance? And we say if node is equal to target, right? Well, it's actually not equal to target, and we just say if dp node, so everybody is going to be the shortest distance, right? Everybody is going to be, let's say, math.infinity, right? If db node is smaller than infinity, that means we have checked it already. Right? We try to not. So we say, what do we say? Scene. So a node, we do scene, and I don't think I need to return anything, right? And then, so adjacency, so for child, oh, it's going to be a dictionary, right? So this is adjacency dot items, child and weight, and this if child not in scene, right? Which means the child has not been visited before. And if child not in scene, and then if let's say if dp child is equal to math.inf, so we have never done it before. I don't even need this, right? That means I haven't checked this child before. Then we do DFS child target scene and DP. Right? We check the child, and after we check the child will have been done. Then, right? Then we say DP node equals minimum DP node weight plus DP child. Right, that's the minimum distance, and just my distance towards this distance, right? And if it's not equal to math.inf, then we don't have to go, right? And then blah blah blah. Once we're done, right? Scene.remove, and we're over. Now we add the node, we keep going. When we're done, we remove the node. So like backtracking, right? That's backtracking. Like this, we've considered. So we go back and we're trying to go through another route, right? We're trying to go through another route. And if another route I see this, but it's in DP, that means we already considered it. But hold on, hold a sec. Can we redo this? I'm not sure if I can do this because let's say I go to a different route, right? I go this route, it's all just a whole path. And then I backtrack. I go the other way. And then we go the other way, we hit this one again, right? We hit this one again, hit this node again. But the path is different. Can we really say, I don't know, can we say that? I want to find the shortest path from a node to the end, right? And I have these children. And from this one, I want to find all, right? But I want it to be not hitting S1 or S2. That's the goal, is to not hit S1 or S2. Maybe we'll go back to the one that I've seen before. Because the path is different. Let me think again. So going from here, we have a path leading to, right? If I have another path going back here, but we have a smallest path. Hold on, if we have found a smallest path, and if I encounter this node again, what if this smallest path, we quite go this and this, I say that's the smallest path, and I hit this one again, and I have this one, but it's not on my path, so I say I want to visit this one. But this one is the smallest path going this and this, right? Which means the smallest is to go back to me, and then here. Isn't that fine? And I feel like this might be okay. Yeah, this might be okay. So if I have found the smallest path before, and now I'm going here, well, under the previous situation, the smallest path. That's the thing, is that maybe the current path will be even smaller. Right? Let's say the clearest path is from this coming down to you, and I found the smallest path. I cannot go through all these nodes. Now I come to you, that you can go through the previous nodes, right? Yeah, that's the thing. You could come down here, you can go back and to a destination. So that's when it's faster. If you come here, you can't. Then this has to redo, right? We have to rerun the entire thing. The smallest path. Yeah, that's what I struggle with, because each time when I reach a node, the state is different. State is different. No, I'm got stuck. Yeah, that's the question. What if I go back actually can lead me to a better result? Right? If I come here, if I go to one of the previous node, and then I go to, well, lead me to a better situation. Well, we can go from here to there, right? If I can go back to one of the previous node, then from that previous node, then the shortest distance from the previous node is just go directly there. I don't have to go through this, which means if I have found the shortest for this, I might not even go through this. Huh. Let's just say this one works. This should prevent it from going back. And then if this is equal to this means I haven't done, then I need to check. What's the end situation if node equals to target? Right? Just if node is equal to target, now just return. There's nothing we can do. Don't do it. Then this one doesn't do anything. Oh, we don't have to because the target I will set it up will be 0. Target will be 0. Child not in scene, so I have not gone to the child yet. What's the point of finding target? I'm not even using target. Right? I'm not even using target. So this like say from node to DFS to a target. What's the other one that you want to run? Is from S1. So this will be just def DFS source. Right? From source just to go through every single thing. So it's also node scene DP. Okay. So how does this one go? Every time we hit something, I want the shortest distance from this to every node, right? So in the current weight, it's not current weight, total weight so far. So what do? We say again scene.add node, right? And then for child weight. So we current node. So we add this node. And then I also know the total weight of reaching my node. So I need to say dp node should equal to minimum dp node and the total weight. So just assign the new thing. And then we're going for child in adjacent. Oh my god. Node. Alright, adjacency list node.items. So all its children. Right. Then again, if child is not in scene, if it has not been seen before, then I can do DFS source child scene dp total weight plus weight, right? I'm just trying to go through every single one, and then
now or wait 7 minutes.
Now, I think I can wait 7 minutes. See you find a new use of my chopstick.
Burn my hair. I don't have a comb.
Awesome. Okay, so that's that. That is not once. I just had to go through all possible. Child not in scene and and if child, current weight to the child. So like if I go to this child, if I go to this, if the weight to this child is already small, then current weight plus, then we don't even have to go there, right? Now this one can take a while to run. This is not ON because each node can be visited multiple times. So I want a total. Yeah, this is not right. I don't know. Okay, I want to find the shortest path between two nodes. Help us. Yeah, I feel this one's gonna run a long time. Cause I don't think I can stop if it's. Yeah, I cannot stop. I have to update all the nodes. And there is a shorter path. Uh, let's check. I give up. 3 Dijkstras. On the reversed graph. Reverse Dijkstra. What? Oh man, that's just... Alright. What is Dijkstra? Dijkstra is find the shortest path with weight. How did I not think about this? That's what Dijkstra is. To find the shortest path with weights. And this is exactly what we want, right? We want S1 to an X, S2 to an X. I think these are the... Wait, hold on. Don't we have to check every single one? This is an array. Oh, this one is to get... Wait, hold on. What is this? What is Dijkstra? We have a Q, right? We have a Q. Q 0 and K. So we always pop out the current with the smallest time. I think K is a starting point. Okay, K is a starting point. And we set the K to 0 as the starting point. And we pop it out. That's the starting node. T is the, I want to say, the T is a hash map to record the time. So we pop the front. If node has not been visited, T node is the current time to reach the node. And then we get all of its children and to push, cat push the Q, which means the current to reach all these V needs this time, right? It needs all this time. And we pop the top. If this is the visited, we'll take this amount of time. And then for each one, so this one basically, we go through all this, we can record the time needed to go from K to every single node. This is exactly what I'm trying to write. The minimum time needed to go through S1 to every single node. The time needed from S2 to every single node. And then this is from destination, reverse from destination to every single node. So now we just go from every single node. So this go to this. Oh, freaking awesome. So that is how to write Dijkstra. One Dijkstra. I'm gonna check that one too. Yeah, it is reverse. I never thought about the reverse. Because I thought about S1 to every single one, S2 to every single one. And I was trying to find from everyone to the end. But it's the same as from the end to every one. Oh my god. It is 3 Dijkstra. How about this? 1 Dijkstra. Ah, Dijkstra. Mm-hmm. Yeah, this is the key. If the node has already been visited as a type 2 node, if it has already been visited as a type 2 node, which means it's on the other path already, but now on a type 1, it's a type 1 node because the previous one is a type 1 node, right? That's why it's a type 1 node, because it trailed by type 1 node. But it says that it has already been visited as a type 2 node. So it's the type 2 node. But it is also supposed to be a type 1 node. But it has been visited as a type 2 node. So this must be a type 3 node. Okay. Then we update this. Okay, it's named by type 3. Oh my god, this is very good. Bravo. Oh, Dijkstra. Shoot, Dijkstra. 3 Dijkstras. I think it's a shame that at my current stage I still cannot write a Dijkstra from scratch. No, I can't. It's just something, I don't know. I just can't do it. Can't solve this because my dumbass didn't realize that finding the shortest, finding the path with the minimum weight is Dijkstra. Below, I will reproduce the popular solution of 3 Dijkstras. But this solution, Dijkstras, I'll put the reference. However, this solution provides uses only one Dijkstra. Okay, let's try Dijkstra. Okay, so what do we want? We want to first turn this graph, produce 2 graphs. First, produce 2 graphs, one in the original order and the other reversed order. So we can say G1, G2. They both wait, what do we want this one to be? So we just want a path, right? That's what we want. Yeah, let's just go default dict, and default dict, right? And then from to weight in edges, G1F. If T not in G1F, T equals W, else, why do I do this? What does he do? A list, or just append? Wait, you don't worry about oh, I see. You don't have to. Okay, okay. I agree. This is a we will have deal with this anyway. Okay, the list. Now I'll make it easier. So G1F dot append. Let's say T and W. G2T dot append. That's the reverse. F and W. All right. So this is reverse. All right. Now we need to create def Dijkstra. Alright, let's try to see if I can write Dijkstra myself. So we need a graph and the start. Alright, and we're not returning anything. So what do? Dijkstra requires a queue, and we also require a times. Right, so times. So Q is just going to be this. Time. Q is actually going to be time and the start. Time is just going to be a dictionary, right? And then when you say import heap Q. So here's what we're going to do. While Q T node equals heap Q dot heap pop. Q, right? And we say if because it's always increasing. So if T has already been visited, then we don't visit again, right? That's the idea. Yeah, because the first time we visit, if we go some other way, and then if T has been visited before, but if now we have a smaller, shouldn't I update the T? But I don't. Why? What if I find... I do not have a good understanding of Dijkstra. vertex in queue with a minimum distance, okay? For each neighbor of you still in queue. So not visited. We'll have a pre. I want to try to find the actual path. For each neighbor v, yes, if it's smaller, then yes, that's the thing. How do we decrease priority? We'll just push it in, right? So this is saying we have a current node. Now we find all its neighbors, and we just keep pushing it in, right? Keep pushing in, and then if it pops out, right? If it pops out, if it's smaller, then we have to keep going. If it's larger, then we don't keep going. So I don't think this is correct. If node not in T, if it's not in T, and what if it's in T? How do you guarantee that's always the smallest? Because we just keep pushing, or keep pushing time in the V. We can push, let's say, another time, but it's actually smaller. If node not in T, this is recorded the smallest time, right? And every time I pop out is the current smallest for the node. If it's larger then we don't do it. But if it's smaller, then we have to do it again because it can be smaller. Which just means like the first time, yeah, it could be the first if it's not in T. Then we record current time, and then we find a neighbor, and so the neighbor has a large time. And go back, it's not in T, right? And we keep going, and then we go through another one. Now, I don't think this is correct. I don't think this is correct. How is this correct if no, not in T? I need a definitive answer. I have my understanding of this. I don't think it's not guaranteed to be the smallest the first time you encounter it. It could be, right? It's like we'll go around, so that would be the first time we encounter. Second time, no, I will do my way. I will say if a times.get node math.inf, right? If this is larger than the current t, then times node will equal to t, right? And then we basically visit the node again, because the node needs to be visited again if it's smaller, which means for I don't know, child and weight in graph node dot get node, right? Dot get node and this for child and weight in this, then we simply say heap q dot heap push. We're going to push to the queue. What do we push to queue? Current time plus weight, t plus weight, and the child. Right? So we can push, 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 go back to the queue, get out. So once we're done, we're going to return a list. A list of integer, basically. Right? And we say here, I'm going to return for key. For I in range n times.get I. If I is not available, then going to be math.inf. Alright? So that's my Dijkstra. My Dijkstra. And now we're going to say S1 to all, right? S1 to all equals, call it Dijkstra G1. Start will be source 1. S2 to all equals Dijkstra G1 source 2. And then dest to all equals Dijkstra G2 destination, right? Destination to all. And then just go through, just say for I in range n, I want to find S1 to all, right? S1 to all I plus S2 to all I, right, plus D destination to all to I. And then we want to find the minimum of this, right? Minimum of this. So res will equal to minimum of this, and then return res if res is smaller than math.inf, else -1. Try it. And we pass. Oh, this one's tough. Oh, I didn't even. Let me try the wrong answer I have yesterday. right? Okay. We pass. What's Dijkstra? O edge log edge? O n log e. Now I realize. O e log e. O e log v. I'm just gonna go O e log v. O e log v as according. O e log v actually plus we have also a on check. Oh, but we have on here as well. Wait, it should be O e log e, right? We check every single edge. Yeah, don't worry. Wikipedia. Alright, that'll be it. Wow, this is a tough one. I'll see you guys very soon. Adios.